We know the speed of light. We have measured it with instruments so precise that the margin of error is smaller than a human thought. In a vacuum, light travels at exactly 299,792,458 meters per second. This number is not an approximation. It is not a best guess refined over centuries of increasingly careful measurement. It is a definition. Since 1983, the meter itself has been officially defined in terms of the speed of light, meaning the two values are mathematically locked together in a relationship so fundamental that questioning one is questioning the other. The speed of light is the most precisely known physical constant in all of science, and built on top of that single number, like an entire civilization constructed on a single brick, is the light year. The distance light travels in 1 Julian year, exactly 9,460,730,472,580,800 meters. A number so large it dissolves into abstraction the moment you try to hold it in your mind. We use it casually. Astronomers write it in papers, teachers draw it on chalkboards, documentaries whisper it over slow panning shots of spiral galaxies. We have made peace with the light year. We have accepted it as simply the unit of measurement the universe chose to operate in. We assume that because we can name it, because we can calculate it, because we can point a telescope at a star and say with confidence that it sits exactly 24 light years away, we somehow have a relationship with that distance. That familiarity has bred a quiet, deeply irrational comfort. And that comfort is the first thing the true nature of a light year destroys. And then there is the arithmetic of imprisonment. The nearest star system to our own is Alpha Centauri, a triple star system sitting 24 light-years from the Sun. This number sounds manageable, modest even, compared to the billions of light-years we throw around when discussing the observable universe. 4 light-years. Surely a civilization capable of splitting the atom, of landing machines on other planets, of encoding the entire sum of human knowledge onto devices small enough to fit in a pocket, surely such a civilization could bridge 4 light-years. The fastest spacecraft humanity has ever launched is Voyager 1. It is currently moving at approximately 17 kilometers per second relative to the Sun, making it the most distant human-made object in existence. At that speed, Voyager 1 would reach Alpha Centauri in approximately 73,000 years. 73,000 years. The entirety of recorded human civilization spans roughly 5,000 years. We would need to repeat the whole of recorded history 14 times over, back to back, without interruption, without collapse, without forgetting, just to arrive at the doorstep of our nearest neighbor. And Alpha Centauri is the closest thing to us in the entire galaxy. The Milky Way itself is approximately 100,000 light-years in diameter. The Andromeda Galaxy, our nearest galactic neighbor, sits 537 million light-years away. The observable universe stretches 93 billion light-years across. At Voyager speed, a journey across the observable universe would take longer than the current age of the universe by a factor so large the number has no name in common language. The mainstream response to this is propulsion. We simply need faster engines, fusion drives, antimatter rockets, solar sails pushed by focused lasers. Theoretical physicists have sketched out propulsion systems capable of accelerating a spacecraft to a meaningful fraction of the speed of light, perhaps 1/10, perhaps 1/5, perhaps in the most optimistic scenarios, 1/2. At 10% of the speed of light, the journey to Alpha Centauri takes 42 years. A human lifetime? Barely, but conceivable. At 50%, it takes just over 8 years. At 90%, relativity begins to compress time for the travelers, and the journey might feel subjectively shorter. This is the story we tell ourselves. The story of engineering our way out of the prison, and it fails on every level that matters. The first failure is energy. The rocket equation is one of the most demoralizing relationships in all of physics. To accelerate a spacecraft to a higher fraction of the speed of light, you do not need proportionally more fuel. You need exponentially more fuel. At 10% of light speed, the fuel mass required to accelerate a modest crewed spacecraft already exceeds anything humanity has ever engineered by orders of magnitude. At 90% of light speed, the energy required to accelerate even a small probe, not a crewed vessel, not a generation ship, but a small robotic probe, is comparable to the total energy output of the Sun over thousands of years. Antimatter, the most energy-dense fuel theoretically possible, would require quantities that exceed the total amount of antimatter humanity has ever produced, which is measured in nanograms by a factor so extreme it reads as comedy. The energy barrier is not an engineering challenge. It is a physical wall with no door. The second failure is time. Even at relativistic speeds, even exploiting the time dilation that compresses subjective travel time for the crew, the universe outside the ship continues aging at its normal rate. A crew traveling to a star 1,000 light-years away at 99% of light speed might experience only a decade subjectively. But when they arrive, 1,000 years will have passed on Earth. The civilization that sent them will be unrecognizable. The people who love them will be dead for 970 years. Communication during the journey is almost meaningless because signals also travel at light speed, meaning updates from home arrive years apart, and any response takes years to return. An interstellar civilization cannot function, not because of a lack of will or resources, but because the speed of light makes coherent communication across stellar distances structurally impossible. You cannot run an empire when a question takes 1,000 years to receive an answer. The third failure is the destination itself. We have identified thousands of exoplanets. We have found worlds in habitable zones, worlds with atmospheres, worlds with the chemical signatures of potential biology. But nearly every one of them sits at distances measured in dozens, hundreds, or thousands of light years. The closest potentially habitable exoplanet is Proxima Centauri b, orbiting within the habitable zone of the nearest star. It sits 24 light-years away. To send a probe there and receive its first transmission back takes a minimum of 48 years, and that assumes the probe travels at light speed, which no physical object can. Any mission to any confirmed habitable world beyond our immediate stellar neighborhood requires timescales that exceed not just human lifespans, but the duration of human institutions. Universities do not survive 1,000 years unchanged. Governments do not survive 10,000 years. The organizational continuity required to send a generation ship to a distant star, maintain contact with it, and receive its findings does not exist in any human institution ever recorded. The fourth failure is what physicists call the interstellar medium. Space is not empty. Between stars, there exists a thin but real scattering of gas, dust, cosmic rays, and radiation. At low speeds, this medium is harmless, essentially invisible. At relativistic speeds, it becomes catastrophic. A hydrogen atom, struck by a spacecraft traveling at 90% of light speed, carries the energy of a high-powered rifle bullet. The interstellar medium contains approximately 1 hydrogen atom per cubic centimeter on average. At relativistic speeds, the accumulated impacts would shred any known material. The shielding required to protect a crewed vessel traveling at a significant fraction of light speed adds mass. An added mass requires more energy to accelerate, which creates a feedback loop that collapses every proposed design. The interstellar medium is an invisible wall that makes relativistic travel not merely difficult, but physically destructive at the speeds required to make it meaningful. The proposed solutions arrive in sequence and dissolve in sequence. Warp drives, the Alcubierre metric, the idea of compressing space in front of a vessel and expanding it behind, theoretically allow faster than light effective travel without violating relativity because the ship itself never moves through space. Space moves around it. The mathematics permit it. The physics may not. The energy required to create and sustain an Alcubierre bubble has been calculated at various times to require the Massenorgy equivalent of the planet Jupiter. Then revised to smaller amounts, then revised again, with each revision still landing at figures so far beyond any conceivable engineering that the exercise feels less like physics and more like creative accounting. Additionally, recent theoretical work has suggested that the exotic negative energy required for the bubble may not be physically realizable, existing only as a mathematical object with no corresponding phenomenon in nature. Wormholes, traversable shortcuts through spacetime connecting distant regions, fare similarly. General relativity permits them mathematically. Maintaining them against collapse requires exotic matter with negative energy density. No such matter has ever been observed. Quantum mechanics suggests that any wormhole stable enough to traverse would be microscopically small and violently unstable, collapsing faster than any signal could pass through it. The theoretical machinery for faster-than-light travel exists on paper and appears to collapse the moment physical reality is consulted. Generational ships, vessels designed to carry self-sustaining populations across centuries of travel, face a different category of failure. Genetic diversity requirements for a viable founding population are estimated at several hundred to over 1,000 individuals, minimum. The psychological literature on isolated closed communities is consistent and grim. Social cohesion in sealed environments degrades across generations. Purpose attenuates. The descendants of the original crew share no personal connection to the mission their ancestors volunteered for. Mutiny, population collapse, cultural drift, and the compounding of genetic defects in small closed populations are not hypothetical risks. They are documented outcomes of small isolated communities on Earth, under conditions vastly more forgiving than a sealed vessel in deep space. And so we arrive at the silence. The Fermi Paradox asks why, in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them billions of stars, many of them billions of years older than our own sun, we have detected no sign of any other technological civilization, no radio signals, no megastructures, no evidence of stellar engineering, no probe in our solar system, nothing. The standard responses, the zoo hypothesis, the dark forest theory, the idea that civilizations destroy themselves, all of these assume that civilizations capable of interstellar expansion exist, but choose not to expand or are prevented from expanding by their own nature. But the light year offers a different answer. One that does not require malice, silence, or self-destruction. It simply requires physics to be exactly what it appears to be. If the speed of light is an absolute limit, if exotic matter does not exist, if wormholes cannot be stabilized, if the energy requirements for relativistic travel cannot be met, then every civilization in the universe is sealed inside a bubble defined by how far light can travel in the span of that civilization's existence. The universe is not a shared space. It is an uncountable number of isolated cells, each containing one civilization, each separated from every other cell by distances so extreme that crossing them would require either breaking the laws of physics or enduring timescales that no organized society has ever survived. The observable universe is 93 billion light-years across. Our galaxy alone is 100,000 light-years in diameter. The fastest we have ever moved anything is a fraction of a fraction of a fraction of the speed of light. The energy required to reach even a small fraction of that speed for a crewed vessel exceeds anything our civilization has ever produced. And the speed of light, the one number that might save us if we could match it, is the same number that defines the prison, because even at light speed, the nearest galaxy takes 2.5 million years to reach. We named the distance light travels in a year and called it a unit of measurement. We built observatories to count how many of them separate us from other stars and called it astronomy. We wrote equations describing how space-time might be bent to shortcut those distances and called it theoretical physics. And in all of that naming, counting, and calculating, we did something quietly and perhaps unforgivably optimistic. We convinced ourselves that understanding a cage is the same as having a key. The light year is not a unit of distance. It is a unit of impossibility, dressed in the clothing of measurement, sitting in our textbooks with the patient stillness of a thing that knows it has already won. Every star you have ever seen in the night sky is unreachable. Not difficult, not expensive, not a matter of political will or scientific progress or sufficient funding. Unreachable in the same way that yesterday is unreachable, structurally, permanently, by definition. The universe is vast beyond any scale the human nervous system was built to process, and it is almost certainly full of wonders. And we will never reach any of them, and neither will anything that made us, and neither will anything we make, and the stars will continue their slow burning across distances that mock the very concept of travel, indifferent, ancient, and profoundly, perfectly silent.